Dear students, today we will study about AC machinery fundamentals. First of all, we will discuss about some introduction, and then we will cover the first section of the third chapter, a simple loop in a uniform magnetic field. It has two subparts. One part deals with the voltage induced in a simple rotating loop, and we will discuss this in this lecture. And the next subpart deals with the torque and force applied on the rotating loop, that we will discuss in next lecture. After first section, we will go to the fourth section of third chapter, which is induced voltage in AC machines. And after discussing these two sections, then the rest of the sections would be discussed in coming lectures. So first of all, we know that a machine can be given a name to generator as well as to a motor. So a machine can be a generator that converts mechanical energy to electrical energy, or it can be a motor that converts electrical energy to a mechanical energy. So, so every machine is made up of two parts. One part is named as stator, which is the outer part of the machine and is always stationary. That's why it is called stator. You can see in the diagram, this is the outer part of the machine and it is stationary part of the machine. So this is called stator. Another part of the machine is rotor, which is the inner rotating part of the machine, and you can see in the figure that this is the part which rotates in the stator. If we talk about the types of windings, there are two main types of windings in a machine. One is the field winding. The field winding is winding which produces main magnetic field in AC machines. You can see in the diagram that the field winding is located on the rotor. Therefore, the field winding is also known as rotor winding. Now if we talk about the armature winding is the winding where the main voltage is induced. Since this winding is located on the stator, as you can see in the figure, that's why it can also be known as armature winding or a stator winding. Now we classify the AC machines into two types. First class is synchronous machine and the second class is induction machine. In synchronous machine, the current is supplied by DC power source, and in induction machine the current is supplied by the magnetic induction. So this is the main difference. Synchronous machines are mostly used as generators, while the induction machines are mostly used as motors. Now we go to the first section of the third chapter, a moving loop in a uniform magnetic field. There's a AC generator in which the field is fixed but the armature is rotating. This is the another diagram which shows that the armature is rotating but the magnetic field is fixed. And this rotating armature, as you can see, this rotating armature in the diagram, this produce the alternating current in these wires. And the brushes, these two brushes, or you can see these blue brushes attached with the armature, are used to remove the charge from the rings or armature and produce the AC current in the circuit. Now there is a counter question, and this is a food for thought for you, that will it work as AC generator if the armature is fixed and field is rotating? You have to think about this, whether this is possible or not. Now we see a DC machine where armature is rotating and the field is stationary. Now another machine which is the AC machine in which armature is stationary but the field is rotating inside the armature. So these are two poles rotors. Now we come to the wire, a moving conductor wire, where a voltage is induced in a magnetic field. The magnetic field in this diagram is represented with B, and the direction of B is into the paper. The voltage induced in a wire moving in the magnetic field can be found by Fleming's right hand rule, and it would be equal to V cross B, and it would be scalar multiplied with length vector L. The direction of the induced voltage factors can be obtained by Fleming's right hand rule. The thumb, forefinger and middle finger of the right hand are extended at right angles to each other to find the direction of L, V and B. If the index finger points in the direction of flux and the thumb indicates the movement of conductor, then the middle finger shows the direction of EMF induced in this conductor. A simplest possible machine that produces AC voltage is a simple loop of wire rotating within a magnetic field, fixed magnetic field, which is in this case represented with N and S, north and south poles. The magnetic field B is from left to right. As you can see, the lines, dotted lines, starting from left and going towards the right. And then there is a loop, and the top of the loop is shown in this figure. If we want to see the structure of the loop, we can see over here in the second diagram. This is a rectangular loop which has four corners represented with A, B, C and D. Then the central point, a pivot point around which this ring rotates, is represented with O, O bar. And if we see this ring from the top, you can see this ring is present in the magnetic field, and it has some direction of the velocity which is represented with V AB and V CD. The side VAB has a velocity going somewhat upwards, and the side CD of the loop is going slightly downwards, and the loop is rotating in counterclockwise direction, as it can be seen from omega m, which is the rotational velocity of this ring. Now there is the radius of this ring represented with small r. You can see that this small r is also represented in the right diagram, as well as you can see this r in left diagram. This starts from the origin OO bar and ends at the one corner of the loop. Now you can see the segment AB and CD are perpendicular to the plane of the paper, and segment BC and DA are parallel to the plane of the paper. The magnetic field is constant, pointing from left to right, as we have discussed earlier, and the loop rotates in the counterclockwise direction in this case, and the voltage will be induced in this loop. The induced voltage would be, as already discussed, V cross B and scalar multiplied with L. Now we will see this mechanism in detail. When the loop rotates in this magnetic field, a voltage will be induced in it. Now we calculate the voltage on each segment of the loop and then add them up to find the total voltage induced. First segment which we consider is AB segment of the loop. Voltage AB is equal to V cross B into L. V cross B can be written as VB sine theta. Now the direction of V cross B is into the page. And the direction of L is also into the page. That's why the dot product would be VBL sine theta AB, where theta AB is the angle between V and B, as you can see this from the right diagram. Now we calculate the value of voltage induced on the CD or DC segment of the loop. Similarly, in this case, EDC would be VBL sine theta CD, and in this case the direction would be, the direction of V cross B would be out of the page. But we know that since the direction of V cross B is perpendicular to L in the case of CB and AD sections, so the induced voltage in these two segments would be 0, because cos 90 would be 0. So the whole product would be, whole induced voltage would be 0. As discussed earlier, now we again show that it is total voltage induced would be equal to sum of induced voltages of every segment. Two of them would be equal to VBL sine theta, while the other two would be equal to 0. So the sum would be 2 VBL sine theta if we consider that theta AB and theta CD can be related by theta AB is equal to 180 degree minus theta CD, because they are out of phase by 180 degree. But we know that sine theta is equal to sine 180 minus theta. If we know this formula, we apply this formula to our case, and then we can also write that it can be written as 2 VBL sine theta. And in this case, we have added induced voltages of all the segments. The resulting voltage E induced can be seen in the sinusoidal waveform as a function of angle. As the value of angle changes, the sinusoid of the voltage changes. At theta pi by 2, the voltage would be maximum, and at theta 3 pi by 2, it would be maximum in opposite direction, or you can say it would be minimum. So you can see in this sinusoidal diagram, if you want to find the maximum induced voltage, then you have to put the sine theta equal to 1. If we substitute this equal to 1, then the induced voltage would be equal to, maximum induced voltage would be equal to 2 VBL. Another way to express the equation is in relating the behavior of single loop to the behavior of larger AC machines. If the loop is rotating at a constant angular velocity omega, the angle theta of the loop will increase linearly with the time. Theta would be equal to omega t, where omega is the angular velocity and t is time in this case. As you can see, the tangential velocity v of the edges VAB and VCD can also be expressed as V is equal to R omega, where R is the radius of the loop and omega is the angular velocity of the loop. If we say that V is equal to R omega, then E induced, which we have already obtained, can be written as 2R omega BL sine omega t. Now what we have done, we have just substituted the values of theta equal to omega t and V equal to R omega. But from the loop we know that the length is equal to L but the radius is R, and the width would become 2R. If width is 2r, then the area of this loop would be L into 2r. Now we substitute 2rl with capital A representing the area of this loop, and substitute 2rl with A in the equation. After substituting this, we get that the induced voltage is equal to AB omega sine omega t. But as we have already discussed, that AB can be written as the maximum flux in this case. So we can also write that maximum flux into omega sine omega t would be equal to the total induced voltage in the loop. The maximum flux phi max will occur when the loop is perpendicular to the magnetic flux density lines, which are represented with B in this case. The voltage generated in the loop is a sinusoid whose magnitude is equal to the product of flux inside the machine and the speed of rotation of the machine, as can be seen from this above equation. But a third factor would also be considered, which is the number of loops. So if we conclude, we can say the voltage induced in any real AC machine depends on three factors: the flux in the machine, the speed of rotation, and a constant representing the construction of the machine, which in our case would be the number of loops, capital N. Of this lecture, which deals with the induced voltage in AC machines. This is kind of reciprocal to the previous section, as you can see that in this case a rotating magnetic field on the rotor and a stationary coil in the stator is represented in the figure. In this case, basically the magnetic field is rotating while the coil is stationary. You can see from the right diagram that the first portion shows the stator, the next circular portion represents the air gap between the stator and the rotor, and the third part of the circle is rotor, which is in between the first two parts, which is basically the core of this all machine. Air gap flux density is equal to Bm, represented over here the magnetic field, and cos omega t minus alpha. We will discuss one example about this in the next few slides, where the idea would be more clear. In this case, we know that in previous case, as we derived the equation for voltage induced for the case of moving wire, where we had stationary magnetic field, but now the wire is stationary while the magnetic field is moving. But if we go into some frame of reference where the magnetic field is stationary and wire is moving, then the sides of the stator coil will appear to go by a velocity v r. For this, the voltage induced in a single coil, single turn coil is phi omega sin omega t, as we had derived this in previous section. But if we increase the number of coils, if we have, let's suppose, 3 turns of the coil, then the n would be 3 and the 3 would be multiplied with this equation of induced voltage. As written over here, if the stator coil has n turns, then the total voltage induced would be n into phi omega sin omega t, where Nc represents the number of turns in a coil. If 3 coils are there, as represented in the figure, one coil is A bar, another coil is B bar, third coil is C and C bar. We are supposing that we are looking into these 3 coils from the top of the machine. So if 3 coils each of n turns are placed at intervals of 120 degree around the rotor magnetic field, so these 3 coils are 120 degree apart from each other, then the voltage induced in each of them will be the same in magnitude but differ in phase by 120 degree, as it is obvious that the voltage magnitude would be same, but they would be out of phase by 120 degree to each other. Thus, a rotating magnetic field will generate a 3-phase set of voltages in a stator. Let's suppose we say that induced voltage for loop AA bar is equal to n phi omega sine omega t. Then the induced voltage for BB bar and CC bar loops would also have same magnitude, but their angle would differ by 120 degree. As you can see from these three equations that they have a phase difference of 120 degree with each other. The RMS voltage in a three-phase stator. The peak voltage can be found out by including sine omega t as 1, then we will have n phi of omega. If we have n phi of omega, we can write omega in forms of f as 2 pi f, and it would become 2 pi n phi of f. By dividing the equation with under root 2, we can find the RMS value of the voltage. And this under root 2 is basically 2 is divided by under root 2 to give us under root 2 in the numerator, and the equation for RMS value voltage would become under root 2 pi n phi of f. In this case, the RMS terminal voltage of the machine will depend on whether the stator is Y connected or lambda connected, or delta connected. For Y connected machine, as we discussed this Y and delta connections in last lecture, we know that for Y connected machines, V terminal would be equal to under root 3 E of A, which is the RMS voltage, but in delta connected machine, Vt would be simply E of A. It depends on us how the situation is given to us. We will apply accordingly the equation in the problem which we are going to solve. Now we discuss an example which is similar to the previous slide. A diagram is given where there are three loops AA bar, BB bar and CC bar. So this is a two-pole generator, and the peak flux of the rotor magnetic field is 0.2 T, and the mechanical rate of rotation of the shaft is 3600 R per minute. The stator diameter of the machine is 0.5 meter. Its coil length is 0.3 meter, and there are 15 turns per coil. The machine is Y connected. What are the three-phase voltages of the generator as a function of time? In A part, we will find the three-phase voltages of the generator as a function of time. Means that in first voltage we will find sine omega t, In second voltage we will find a phase difference of 120 degree, and in third case we will have a phase difference of 240 degree with respect to the first loop. What is the RMS voltage of this generator? This is the B part. In B part we will find the maximum voltage induced, and then we will divide it by under root 2 and we will find the RMS voltage of this generator. For RMS terminal voltage of this generator, we will use the formula as discussed earlier. As we know that the flux can be easily found out by AB, or you can also find it, or you can also write it as 2RLB, and first of all we find phi and omega so that we can put these values in the formula to find the maximum induced voltage E max, as shown in A part, that E max is equal to n phi omega. We are given that there are 15 turns of the coil, so n would be 15 and the total answer would be 169.7. In the case of three-phase voltages, as we are asked that we should give the three-phase voltages in terms of variable t, so the loop AA bar would have 169.7, and you can see from here that the magnitude of all the three phase voltages is same. The difference is only in the phase. In AA bar the phase is 0 degree, in BB bar the phase difference is 120 degree, and if we compare with AA bar, the CC bar would have 240 degree phase difference. Now we come to the B part of the example, where the RMS phase voltage is calculated by dividing the maximum voltage by under root 2. In the C part, we again use the formula for terminal voltage, terminal RMS voltage, according to the Y connection used in this example. Now these are the voltages of three loops A, B and C. A is the loop which is starting from 0. The value of